Welcome back to the course on superconductivity. Today we're going to talk about hard and soft superconductors. We'll first do a small recap about Type 1 and Type 2 superconductors, then go over the fluxoid definition, see what flux flow is, and then learn about flux pinning. After all these definitions, we'll see the difference between hard and soft superconductors. First of all, Type 1 superconductors are in the Meissner state when they are superconductive, therefore, their magnetization curve is linear until they reach the normal state. The critical field of Type 1 superconductors is usually below 0.1 T, which is their biggest limitation. On the other hand, Type 2 superconductors initially follow the same behavior until their first critical field, denoted Hc1, and then reach the mixed state. In the mixed state, the magnetization curve is nonlinear and decreases as the field increases until reaching zero, where the superconductor is driven to its normal state. While Hc1 is usually lower than the critical field of the Type 1 superconductors, Hc2 tends to be much larger, so Type 2 superconductors are usually good candidates to make magnets. The decrease in magnetization in the mixed state is due to the emergence of fluxoids. Fluxoids can be described through the following key points. Fluxoids are quantized flux that penetrates the superconductor when the applied magnetic field is higher than Hc1. The material is in its normal state inside the fluxoid. A screening current circulates around the normal region to maintain the diamagnetism of the superconducting region. That is why fluxoids are sometimes referred to as vortices. Additionally, vortices repel each other by Lorentz force due to the screening current. Keep in mind that the screening current's direction of rotation depends on the applied field. In the representation here, you can see a slab with the vortex placed in the most compact wafer cylinders, which is a hexagonal lattice. On the right side, you can see a microscopic image of the fluxoid lattice. Now we'll see the flux flow. When a current flows in a superconductor, the vortex experiences the Lorentz force, which will make the fluxoids move. This phenomenon is called flux flow. Furthermore, when the fluxoids move, the magnetic flux they contain is also moving, so from Faraday's law, we have an electromotive force through the normal zone. This will create a non-superconductive current and therefore create losses. Thankfully, fluxoids tend to be electromechanically pinned at defects. This phenomenon is called flux pinning, and it is one of the reasons we can use Type 2 superconductors because as long as the pinning force is higher than the Lorentz force induced by the current, there is no loss of energy. As we saw before, generating a normal zone inside a superconductor within its critical parameters is energetically unfavorable, so vortices tend to get pinned to defects that are already in a normal state. On the bottom right, you can see a video of the flux pinning effect having macroscopic consequences. Here, not only is the bulk YBCO levitating, but it is also staying at a fixed place compared to the magnet. To clarify, if the bulk YBCO was in its Meissner phase, the bulk YBCO would fall off the sides. Now that we know what fluxoids are and their behavior, we can define hard and soft superconductors. Type 2 superconductors with significant flux pinning are considered hard, while Type 2 superconductors with no significant flux pinning are called soft. In the graph on the left-hand side, we can see the effect of having a stronger flux pinning. Sample A has a low pinning force, B is a bit stronger, and C has the strongest. The stronger the pinning force, the higher the critical current of the wire will be. On the right-hand side, we can see that the higher the applied field on a sample is, the steeper the flux flow VI curve will be. Remember that an increasing field in the mixed state increases the number of fluxoids, therefore, for higher fields, a higher number of fluxoids are moving, which means higher losses. This effect can be seen until reaching a field over Hc2, where the superconductor goes to its normal state. The key point to remember from this slide is that hard superconductors have a higher critical current density than their counterpart. To conclude, by definition, hard superconductors are Type 2 superconductors with defects and impurities, as opposed to soft superconductors that are pure with no defects. Hard superconductors, therefore, have a higher critical current density due to the flux pinning effect, which is crucial for applications. On a side note, usually, defects are added on purpose to increase the critical current density. However, since defects replace some volume of the superconductor, there is a limit to how many defects or impurities can be added.